Hello and welcome. Tonight we'll be exploring how quantum mechanics reshaped our understanding of reality, transforming not only science, but also the technologies that quietly guide our everyday lives. Long before anyone imagined quantum computers or atomic clocks, people believed the universe worked like an enormous clock, steady, predictable, and perfectly reliable. It was a beautiful idea, one that seemed to explain almost everything. Yet hidden beneath ordinary experience was a world that refused to obey those familiar rules. So, find a comfortable place to rest, allow your thoughts to slow like gentle waves reaching a quiet shore, and let's begin our journey into one of the most fascinating discoveries in the history of science. For most of human history, the universe seemed reassuringly dependable. Morning always followed night. The moon faithfully returned to the sky. The seasons arrived in their familiar rhythm. Rivers flowed downhill, apples fell from trees, and stars appeared to circle overhead with remarkable regularity. Nature seemed to move with such consistency that many believed the universe itself must be governed by a grand and orderly design. Then, during the 17th century, a remarkable way of understanding that order emerged. Isaac Newton and his contemporaries described the motion of falling apples and wandering planets using the same elegant laws. Suddenly the heavens and the earth no longer seemed like separate realms. Everything appeared connected by a common mathematical language. The universe became something that could be predicted. Imagine rolling a pair of dice across a wooden table. To you, the result feels random, perhaps a 3, perhaps a 6, perhaps something in between. But according to classical physics, the outcome is not truly random at all. If someone somehow knew every tiny detail, the exact force of your hand, the angle of release, the texture of the table, the movement of the air, even the smallest imperfections inside the dice, they could, in principle, calculate exactly how the dice would land. It would be an unimaginably difficult calculation, but not an impossible one. This idea became known as determinism. The future, according to this view, was already quietly contained within the present. Every event unfolded because of the one before it, like an endless line of falling dominoes stretching across the universe. The same thinking applied everywhere. A pendulum swinging inside a quiet clock, a baseball soaring across a summer field, the graceful orbit of Earth around the sun. Given enough information, every motion could be predicted. The universe resembled an enormous clock built with extraordinary precision, every gear turning exactly as it should. It was an idea that inspired enormous confidence. Engineers built bridges, navigators crossed oceans, astronomers predicted eclipses decades before they happened. The Industrial Revolution flourished because these dependable laws worked astonishingly well. The more carefully people studied nature, the more the universe seemed like a masterpiece of order. For centuries, this picture appeared almost complete, yet beneath that calm surface, tiny cracks had already begun to appear. Scientists started asking questions about things too small to see directly. They investigated heat, light, electricity, atoms. Each new discovery seemed straightforward at first, but gradually strange puzzles emerged. Light in particular became increasingly difficult to understand. Sometimes it behaved exactly like a wave. It spread outward like ripples across a quiet pond after a pebble slipped beneath the surface. It bent gently around obstacles. It produced colourful patterns where waves overlapped, much like circles spreading across still water. Everything suggested that light was a wave, and yet, in other experiments, light behaved as though it consisted of tiny individual packets, arriving one by one like delicate grains of rain falling onto the earth. How could both pictures possibly be true? Was light a wave, or was it a particle? Neither answer seemed complete. The deeper scientists looked, the stranger reality became. The mysteries did not stop with light. Atoms themselves refused to behave like miniature solar systems. Certain colours of light appeared where none should exist. Some forms of radiation could not be explained. Tiny pieces of matter seemed to ignore rules that worked perfectly for planets, pendulums, and falling apples. The familiar clockwork universe was beginning to lose its certainty. It was as though humanity had spent centuries studying the calm surface of a vast ocean, only to discover that beneath the water lay an entirely different world, filled with unfamiliar currents moving according to rules no one had imagined. At first, many scientists believed these puzzles would soon disappear. Perhaps a few missing pieces remained. Perhaps the measurements simply were not accurate enough. Perhaps another small adjustment would restore the comfortable picture everyone already knew. Instead, something far more extraordinary happened. The old picture did not merely need a few repairs, it needed an entirely new foundation. Over the following decades, a new way of understanding nature slowly emerged. It would eventually become known as quantum mechanics. Unlike many scientific theories that describe only a narrow corner of nature, quantum mechanics reached astonishingly far. It explained the behavior of atoms, it explained chemistry, it explained why solids remain solid, why stars shine, why lasers work, why computers can process information, why atomic clocks keep time with extraordinary precision. Today, nearly every electronic device surrounding you depends, somewhere deep inside, on ideas born from quantum physics. Your smartphone, your computer, medical imaging devices, fiber optic communication, GPS navigation. Even some of humanity's greatest astronomical discoveries rely upon technologies built directly from quantum principles. Whether we realize it or not, we already live in what many scientists call the quantum age. That is perhaps the greatest surprise of all. Quantum mechanics is often introduced as something distant, mysterious, and almost disconnected from ordinary life. But the opposite is true. It quietly surrounds us every day. The only reason it feels unfamiliar is because our senses evolved to understand a world much larger than atoms. Our intuition was shaped by trees, rivers, mountains, and falling stones, not by electrons dancing inside atoms or tiny particles of light crossing unimaginable distances. And so, as scientists began exploring this hidden realm, they discovered something both unsettling and beautiful. Nature itself was far stranger than anyone had dared to imagine. The first clue came from something so ordinary that it fills every sunrise, every sunset, and every quiet evening sky. Light itself. It would become the doorway into an entirely new understanding of reality. If there is one thing that seems perfectly ordinary, it is light. It wakes us each morning through the curtains. It paints sunsets across the horizon. It reflects from the pages of a favourite book and allows us to recognise familiar faces. It travels across unimaginable distances from distant stars, carrying stories that began millions or even billions of years ago. For something so familiar, light hides remarkable secrets. For centuries, scientists believed they understood what light was. It behaved beautifully as a wave. Imagine standing beside a peaceful lake just after sunrise. You pick up a small pebble and gently toss it into the still water. Circular ripples spread outward, growing wider and softer as they travel. Two sets of ripples can overlap, strengthening one another in some places while cancelling each other in others. Light seemed to do exactly the same thing. When beams of light passed through tiny openings, they spread out. When two beams met, they created delicate patterns of bright and dark bands, just as overlapping water waves would. Everything pointed toward the same conclusion. Light was a wave. For a long time, that explanation seemed complete. But nature had quietly prepared another surprise. Toward the end of the 19th century, physicists began performing increasingly careful experiments. The instruments became more precise, and the questions became more ambitious. Instead of studying light from the sun or from a candle, they examined how glowing objects released energy. At first, nothing appeared unusual. As an object became hotter, it glowed more brightly. A piece of iron inside a blacksmith's forge slowly changed from a dull red to orange, then yellow, and eventually almost white. The behaviour seemed simple enough. Yet when scientists attempted to describe this process using the trusted laws of classical physics, the calculations refused to agree with reality. Something was missing. In 1900, a German physicist named Max Planck proposed an idea that he himself initially regarded as little more than a mathematical trick. Perhaps, he suggested, energy could not be exchanged in perfectly smooth, continuous amounts. Perhaps nature delivered energy in tiny, indivisible packets. He called these packets quanta, a word that simply means small amounts. At first, almost no one imagined that this modest proposal would become the foundation of an entirely new understanding of the universe. A few years later, another mystery appeared. Albert Einstein was studying an experiment known today as the photoelectric effect. Imagine sunlight shining onto a clean metal surface. According to the classical wave picture, making the light brighter should always make it easier to knock tiny particles called electrons out of the metal. But that was not what happened. Instead, the colour of the light mattered more than its brightness. Some colours, no matter how intense they became, simply could not release the electrons. Other colours accomplished the task almost immediately, even when they were relatively dim. It was as though each tiny particle of light carried its own individual delivery of energy. Einstein suggested something astonishing. Light sometimes behaves not only as a wave, but also as countless tiny particles, each carrying a specific amount of energy. Today we call these particles photons. This idea sounded almost impossible. How could light be both a spreading wave and a stream of tiny particles? It seemed as contradictory as saying that rain could behave like a flowing river, while each individual drop remained separate. Yet experiment after experiment continued to support this strange picture. Sometimes light behaved like ripples spreading across water. Sometimes it behaved like individual grains of sand falling one by one. Neither description alone was sufficient. Nature seemed unwilling to choose between them, and if light possessed this surprising dual character, scientists soon began wondering about matter itself. Could electrons also behave like waves? Could atoms possess properties that had never been imagined? The questions multiplied far faster than the answers. During the early decades of the 20th century, some of the greatest scientific minds gathered to confront these mysteries. One famous meeting took place in Brussels in 1927. Today it's remembered as the Fifth Solvay Conference. Looking at the famous photograph of the participants feels almost unreal. Albert Einstein, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, Marie Curie. Many of the people who had shaped modern physics stood together in a single room, each trying to understand a universe that had suddenly become much stranger than anyone expected. Their discussions were passionate, sometimes respectful, sometimes deeply divided. Einstein, who had helped launch quantum theory, struggled to accept where it seemed to lead. He believed that nature must ultimately remain orderly and complete. He famously remarked that he could not believe God played dice with the universe. Bohr saw things differently. Perhaps uncertainty was not simply a temporary gap in human knowledge. Perhaps uncertainty belonged to reality itself. This was a breathtaking shift in perspective. Return for a moment to the image of rolling a pair of dice. In the classical world, the uncertainty came from us. We lacked enough information to predict the outcome, but quantum mechanics suggested something far more unsettling. Even if we possessed every piece of information that the laws of physics allowed us to know, we still could not predict a single future outcome with complete certainty. Instead, we could only calculate different possibilities and the likelihood of each one. Probability was no longer merely a reflection of human ignorance. It appeared woven into the fabric of nature itself. This idea remains one of the most profound changes in scientific thinking. For centuries, certainty had stood at the heart of physics. Now, possibility took its place. That does not mean the universe became chaotic or irrational. Quantum mechanics is extraordinarily precise. Its predictions have been tested countless times with astonishing success. What changed was not the reliability of science, but our understanding of what science could ultimately predict. Instead of promising a single guaranteed future, quantum mechanics revealed a landscape of possibilities governed by elegant mathematical rules. The deeper scientists looked into the microscopic world, the more this hidden landscape revealed itself. It became clear that tiny particles could no longer be described as simple, little balls moving along perfectly defined paths. Something richer and far more mysterious lay beneath the surface. The familiar certainty of the clockwork universe had quietly dissolved, replaced by a reality that resembled not a single road stretching into the distance, but countless gentle pathways waiting for nature to choose among them. It is within that invisible landscape of possibilities that some of the most beautiful and puzzling ideas in all of science begin to emerge. Imagine standing on a quiet hill just before sunrise. A gentle mist hangs over the fields below. From where you stand, you cannot clearly see the winding paths that cross the landscape. They are hidden beneath the soft blanket of fog. You know the paths are there, but until the mist slowly lifts, countless possibilities seem to exist at once. The quantum world feels a little like that. Once scientists accepted that light could behave in surprising ways, they turned their attention to the tiny particles that make up matter itself. They expected to discover miniature versions of the familiar world, tiny objects moving along tiny paths, much like planets circling the sun. Instead, they found something far stranger. Imagine trying to describe the journey of a single electron. Your everyday intuition immediately asks a simple question: where is it? It seems like the most natural question in the world. After all, if someone asked where a bird was flying or where a train was travelling, you could point to a particular place. Every object around us appears to occupy one location at any given moment. But quantum mechanics offers a remarkably different picture. Rather than describing an electron as following one definite path before it is observed, the theory describes a landscape of possibilities. Physicists represent this with something called a wave function. The name may sound intimidating, but the underlying idea is surprisingly gentle. Instead of imagining the electron as a tiny marble rolling across a table, imagine the ripples spreading across a calm lake after a pebble touches the surface. The ripples do not point to one exact destination. Instead, they spread gracefully across many possible locations. The wave function is somewhat like that. It does not simply tell us where an electron is. It describes where the electron might be found when we eventually look. This is one of the most profound changes in scientific thinking. Nature no longer presents a single road leading toward the future. Instead, it offers a landscape filled with possibilities. At first, this idea can feel deeply uncomfortable. Our minds naturally search for certainty. Surely we think the electron must secretly have one true location. Perhaps we simply have not discovered it yet. For many years, Albert Einstein shared that feeling. He believed the apparent uncertainty must hide a deeper level of reality that science had not yet uncovered. Other physicists, including Niels Bohr, believe something even more surprising. Perhaps there is no hidden certainty waiting behind the scenes. Perhaps the wave function is already the most complete description nature allows us to have. Even today, thoughtful physicists continue discussing this question. The mathematics of quantum mechanics works extraordinarily well. What remains mysterious is how we should interpret what that mathematics is telling us about reality itself. One of the most fascinating ideas to emerge from this picture is known as superposition. The word sounds technical, but the image behind it can be surprisingly simple. Imagine sitting quietly at a piano. Your hands rest gently above the keys. The melody has not yet begun. At this peaceful moment, countless songs remain possible. A lullaby, a concerto, or a simple tune remembered from childhood all exist as possibilities waiting for the first note. Only when the music begins does one particular melody unfold. Quantum superposition is not exactly like this, but the comparison captures something important. Before a measurement takes place, a quantum system is described as containing multiple possible outcomes together, rather than following one clearly defined path that our everyday intuition expects. This does not necessarily mean that an electron is literally everywhere at once, nor does it necessarily mean that it is nowhere. In truth, quantum mechanics itself does not answer those questions directly. It provides astonishingly accurate predictions about what we will observe, but it leaves room for different interpretations about what is happening behind the scenes. That uncertainty has inspired generations of debate, curiosity, and philosophical reflection. Closely connected to this is another famous idea known as the uncertainty principle. The name sometimes leads to a common misunderstanding. It is tempting to imagine that scientists simply need better microscopes or more powerful instruments. But that is not what the principle says. Instead, it tells us that certain pairs of properties, such as a particle's position and its motion, cannot both be specified with unlimited precision at the same time. This is not merely a limitation of our technology. It appears to be woven into the very structure of quantum reality. Nature itself refuses to reveal every detail all at once. Surprisingly, this does not make the universe less orderly. It simply means that order exists in a different form than our everyday intuition expects. As beautiful as these ideas are, they raise another puzzle. If tiny particles can exist in these delicate quantum states, why does the world around us seem so solid and ordinary? Why does a cup remain comfortably on the table instead of appearing in several places at once? Why does the moon continue shining peacefully in the night sky whether we look at it or not? The answer may lie in a process known as decoherence. Fortunately, the idea is much less intimidating than the word itself. Imagine dropping a single clear note into a silent concert hall. For a brief moment, the sound is pure and distinct, but gradually it bounces from walls, seats, and ceilings, mixing with countless tiny echoes until the original note becomes impossible to separate from its surroundings. Something similar happens to quantum systems. Tiny particles are never completely isolated. They constantly interact with light, heat, nearby atoms, and the countless influences of their environment. These interactions gently erase the fragile quantum relationships that allow superposition to remain visible. It is not that quantum mechanics suddenly stops working. Rather, the delicate quantum behavior becomes spread throughout the surrounding world so quickly that it effectively disappears from ordinary observation. This is why everyday objects behave so differently from individual atoms. The chair beside you is built from unimaginably many particles, all interacting continuously with their environment. Its quantum behavior becomes hidden beneath this constant exchange with the world around it. The tiny quantum landscape remains present, but it no longer appears directly in our everyday experience. Scientists continue performing remarkable experiments that push this boundary ever further. Over the years, they have observed wave-like behavior not only in electrons, but also in atoms and increasingly complex molecules, suggesting that quantum mechanics is not a special set of rules reserved only for the smallest particles. Instead, it appears to be the foundation upon which the entire physical universe is built. Our familiar classical world may simply emerge naturally from this deeper quantum reality, much as calm ocean waves emerge from the countless tiny motions of individual water molecules. The closer we look, the clearer it becomes that certainty is not the deepest language of nature. Possibility is. And as extraordinary as that realization may seem, an even greater surprise was quietly waiting. Some quantum particles do not merely share possibilities, they appear to share one another's very existence, remaining connected across astonishing distances in ways that once seemed impossible to imagine. By now, the quantum world has already invited us to let go of one familiar certainty. Tiny particles are not always described as following a single, perfectly defined path. Instead, they inhabit a landscape of possibilities that only gradually becomes clear through observation. Remarkable as that idea may be, it is not the strangest lesson quantum mechanics has to offer. There is another phenomenon that has puzzled scientists for nearly a century, one that even Albert Einstein found deeply unsettling. It begins with something wonderfully ordinary. Imagine that you and a close friend each have a beautifully crafted coin. Before saying goodbye, you place the coins into separate wooden boxes. Your friend boards a train and travels to another city carrying one box, while you remain at home with the other. Days later, you open your box and discover that your coin is showing heads. Instantly, you know that your friend's matching coin must be showing tails. There is nothing mysterious about this. The two coins were arranged before you separated. You simply did not know which side your own coin was showing until you looked. Now imagine something very different. Suppose neither coin has decided which side it will show before the boxes are opened. Suppose that only when one box is opened does the outcome become definite, and at that very same moment, the distant coin somehow reveals a perfectly related result, no matter how far apart the two boxes may be. That sounds less like physics and more like the beginning of a fairy tale. And yet, the quantum world seems to behave in ways that gently resemble this astonishing picture. This phenomenon is known as quantum entanglement. The word itself can sound intimidating, but its meaning is surprisingly poetic. To become entangled simply means that two quantum particles are described together as parts of one shared quantum system, rather than as completely independent objects. It is almost as though nature remembers that they once belonged together. This does not mean invisible strings stretch across space, nor does it mean that secret messages race between the particles faster than light. Those images are appealing, but they are not what quantum mechanics describes. Instead, the connection exists in the mathematical relationship between the particles themselves. Although they may travel to opposite sides of the Earth, or in principle, even much farther, they continue to be described by a shared quantum state. For many years, this idea felt almost impossible to accept. Albert Einstein famously referred to it as spooky action at a distance. The phrase has become one of the most memorable quotations in the history of science, not because Einstein believed it, but because he hoped it could not possibly be true. He suspected that quantum theory was incomplete. Perhaps he suggested hidden information already existed inside each particle from the moment they separated. If scientists could only discover these hidden instructions, everything would once again appear orderly and predictable. It was a thoughtful and reasonable idea. For decades, physicists searched for ways to test it. The challenge was extraordinary. How do you distinguish between a universe governed by hidden instructions and one governed by genuinely quantum relationships? The answer began to emerge through the work of a physicist named John Bell. Bell developed a remarkable way of comparing the predictions made by hidden variable theories with those made by quantum mechanics. His work transformed a philosophical debate into something that could be tested experimentally. That was a profound achievement. Science advances not simply through imagination, but by asking questions that nature itself can answer. Over the following decades, increasingly sophisticated experiments were carried out in laboratories around the world. Pairs of entangled particles were created and sent toward detectors separated by ever greater distances. Again and again, the results agreed with quantum mechanics. Again and again, the hidden variable explanations that Einstein had hoped for struggled to survive these careful tests. Today, entanglement has become one of the most thoroughly examined phenomena in modern physics. That does not mean every mystery has been solved. Far from it. Physicists continue debating what entanglement ultimately tells us about reality. But there is little doubt that the phenomenon itself is real. The universe truly allows particles to share relationships, unlike anything found in ordinary experience. Perhaps the most helpful way to picture entanglement is not as two separate objects communicating with one another, but as one larger object extending across different places. Imagine listening to a beautiful duet performed by two musicians. One sits quietly at a piano, the other gently plays a violin. Although the instruments produce different sounds, the music belongs to neither performer alone. The melody exists because of the relationship between them. Trying to understand only one instrument would never reveal the complete composition. Quantum entanglement is similar in spirit. The individual particles matter, but the relationship between them becomes equally important. Once scientists learned to create and control these delicate relationships, remarkable possibilities began to appear. One of the most fascinating is something called quantum teleportation. Despite its dramatic name, it does not transport people from one place to another. No one disappears from one room and instantly appears in another. Instead, quantum teleportation allows the state of one quantum system to be faithfully transferred to another distant system, using both entanglement and ordinary communication working together. The process is subtle, elegant, and entirely different from the science fiction stories that first come to mind. Closely connected to this is another important principle. Quantum information cannot simply be copied perfectly. This is known as the no-cloning theorem. While the name sounds technical, its consequence is surprisingly intuitive. Nature places limits on how quantum information can be duplicated, preserving the delicate structure that makes quantum systems unique. Rather than becoming an obstacle, this limitation has inspired entirely new technologies. Imagine sending an important handwritten letter across the world. You might worry that someone could secretly open the envelope, read the contents, carefully seal it again, and leave no trace behind. Quantum communication offers a remarkable alternative, because observing quantum information inevitably changes it in subtle ways. Any attempt to intercept certain quantum messages can reveal that someone has been listening. Instead of relying only on clever mathematics to protect information, security begins to draw strength from the laws of nature themselves. Researchers have already demonstrated secure quantum communication across cities, between mountaintops, and even between satellites orbiting high above the Earth. The dream of a future quantum internet is slowly taking shape. Unlike today's internet, which moves classical bits of information, a quantum network would also be capable of distributing entanglement itself. Special devices called quantum repeaters may one day help extend these fragile quantum connections across continents, allowing entirely new forms of communication, sensing, and distributed computation. Many technical challenges remain before such networks become commonplace. Quantum states are delicate. They interact easily with their surroundings. Maintaining them across long distances requires extraordinary precision. Yet history has often shown that today's scientific challenge becomes tomorrow's ordinary technology. A century ago, the idea of carrying a powerful computer inside a pocket would have sounded almost magical. Today, millions of people scarcely give it a second thought. Perhaps one day, future generations will think about entanglement with the same quiet familiarity. For now, it remains one of nature's most beautiful reminders that the universe is not always built from isolated pieces. Sometimes, its deepest stories are written in relationships. And while entanglement invites us to rethink connection across space, another quantum discovery quietly transformed something even more familiar: our understanding of time itself, allowing humanity to build clocks of astonishing precision that guide nearly every modern journey. There is something quietly comforting about a clock. Whether it hangs on the wall of a cozy kitchen or rests beside a bed, a clock seems to promise that time moves steadily forward, one gentle moment after another. The ticking may fade into the background of everyday life, yet it quietly shapes almost everything we do. We wake because of clocks. We meet friends because of clocks. Airplanes depart, trains arrive, and people living on opposite sides of the world can speak with one another because humanity has learned to measure time with remarkable precision. Yet our understanding of time has changed dramatically over the centuries. Long before mechanical clocks filled town squares with the sound of ringing bells, people looked toward the sky. The rising sun marked the beginning of a new day. Shadows stretching across carefully carved stones became some of the earliest clocks ever created. Sundials transformed sunlight into a gentle measure of passing hours. Later came water clocks, where tiny streams flowed patiently from one container into another. Then came pendulum clocks. Imagine watching a pendulum swinging back and forth in a quiet room. Left, right, left, right. Its rhythm feels wonderfully dependable, almost like the calm breathing of someone peacefully asleep. For centuries, the pendulum represented one of humanity's finest tools for measuring time. Eventually, quartz clocks arrived. Inside these clocks, a tiny crystal vibrates with astonishing regularity whenever electricity passes through it. Each vibration acts like the steady beat of a tiny drummer, allowing clocks to become smaller, cheaper, and far more accurate than ever before. Even today, countless watches and household clocks still rely on this elegant principle. But scientists eventually discovered something surprising. Neither the Earth nor even the finest pendulum could provide a truly perfect measure of time. Our planet is wonderfully reliable, but it is not perfectly constant. The Earth's rotation changes ever so slightly. The Moon's gentle gravitational pull gradually slows our planet's spin over immense spans of time. The movement of oceans, shifting winds, earthquakes, and even the slow drifting of continents can introduce tiny variations into the length of a day. These changes are incredibly small. Most of us would never notice them. But for modern science and technology, even the tiniest differences matter. Scientists began searching for something more dependable. Instead of looking toward the heavens, they looked inward, toward the atoms themselves. Atoms possess an extraordinary property. Their internal energy can change only in very specific ways. You can imagine these energy levels like the carefully spaced notes of a piano. A piano does not produce every possible sound between two keys. Instead, it offers distinct notes arranged with remarkable precision. Atoms behave in a somewhat similar way. When an atom changes from one energy level to another, it absorbs or releases light with an extremely precise rhythm. That rhythm never depends on weather. It never depends on the seasons. It does not care whether the atom is in a laboratory, on a mountain, or travelling through space. It is part of the atom's very nature. Each kind of atom possesses its own unique rhythm, almost like a musical signature that never changes. Scientists realized they had discovered something extraordinary. Rather than allowing clocks to depend on moving gears or swinging pendulums, why not allow nature itself to keep time? One particular atom proved especially useful. It is called cesium-133. This atom produces a beautifully stable rhythm that scientists can measure with astonishing accuracy. Today, the international definition of 1 second is based on this natural rhythm rather than the rotation of the Earth. In other words, humanity no longer measures time by watching the planet turn beneath the stars. Instead, we listen to the quiet heartbeat of atoms. This achievement may sound like a technical detail, but it quietly supports much of modern civilization. Consider the Global Positioning System, more commonly known as GPS. Most of us think of GPS as a collection of satellites helping us find restaurants, airports, or unfamiliar streets. Yet GPS is really a system for measuring time. High above the Earth, satellites continuously broadcast signals containing extremely precise timestamps. Your phone compares the arrival times of signals from several satellites at once. Because radio waves travel at the speed of light, even an unimaginably tiny difference in arrival time reveals how far away each satellite must be. By comparing these distances, your phone determines your location. The entire process happens in moments so brief that they almost defy imagination. If the clocks aboard those satellites drifted by only a tiny fraction of a second, the errors would grow rapidly. Within a short time, your location could be wrong by many kilometers. The maps that quietly guide millions of daily journeys depend upon clocks so accurate that they lose almost no time over incredibly long periods. Quantum mechanics makes this possible, yet scientists were not satisfied. If atoms could provide one remarkably steady rhythm, perhaps another atom could provide an even better one. This search led to the development of optical clocks. The name simply means that these clocks measure rhythms associated with light itself. Imagine two rulers. One ruler has only a few markings, the other has thousands of tiny, finely spaced marks. Which ruler allows more precise measurements? Naturally, the second one. Optical clocks work in much the same way. Because the rhythm of visible light is enormously faster than the microwave rhythm used in traditional atomic clocks, scientists gain many more ticks within the same amount of time. More ticks mean greater precision. Among the most promising atoms for these clocks is strontium. Its extraordinarily stable rhythm allows measurements of time with breathtaking accuracy. In fact, modern optical clocks are around 100,000 times more precise than many of the atomic clocks that transformed science only a few decades ago. Their precision is so remarkable that they can detect tiny differences in the flow of time caused simply by changing height. Raise one of these clocks by only a very small distance, roughly comparable to the thickness of a human hair, and the change predicted by Einstein's theory of gravity becomes measurable. Time itself flows just a tiny bit differently. That idea would have seemed impossible to the generations who once relied on sundials carved into stone. Today, it is quietly measured inside carefully controlled laboratories. These remarkable clocks are becoming much more than instruments for keeping time. They are evolving into sensitive tools for exploring the universe itself. Scientists hope they will help map subtle changes in Earth's gravity, improve navigation without relying on satellites, and perhaps even reveal new clues about the deepest laws of physics. What began as humanity's desire to measure the passing of days has become one of our most powerful ways of exploring reality. And as our clocks grew more precise, they revealed another extraordinary truth. Time is not the rigid, universal river that people once imagined. Instead, it bends gently alongside gravity, while another quantum invention, one built from perfectly synchronized light, would soon allow humanity to hear the faintest echoes of the universe itself. The more precisely humanity learned to measure time, the more we began to notice that time itself was not quite as rigid as we once believed. For centuries, people imagined time as something universal, a great invisible river flowing evenly throughout the cosmos. Whether you stood on a quiet beach, climbed a mountain, or travelled to another continent, time was assumed to pass in exactly the same way for everyone. Albert Einstein revealed a very different picture. According to his theory of relativity, time and space are woven together into a single fabric, often called space-time. Massive objects such as planets, stars, and galaxies gently curve this fabric, much like a heavy stone resting on a stretched blanket. Objects move through these curves not because they are being mysteriously pulled, but because space-time itself is shaped by gravity. This picture is both elegant and deeply surprising. It also carries an unexpected consequence. Time itself does not flow at exactly the same rate everywhere. A clock resting high on a mountain will tick ever so slightly faster than an identical clock closer to sea level, where Earth's gravity is just a little stronger. The difference is incredibly small. No ordinary wristwatch could ever notice it. For generations, this effect remained one of Einstein's beautiful predictions. Then quantum physics quietly provided the tools needed to observe it. As you learned in the previous session, today's optical clocks are so astonishingly precise that they can detect these tiny differences in the passage of time. Raise one of these clocks by only a very small distance, about the thickness of a human hair, and the change becomes measurable. It is a remarkable thought, not because time has suddenly become unreliable, but because the universe is revealing that time has always been more flexible than our everyday experience suggests. To make discoveries like this, scientists needed something extraordinary. They needed light of exceptional purity. Not ordinary light from a lamp, not sunlight pouring through a window. They needed light whose waves moved together with remarkable precision. That invention arrived in the middle of the 20th century. It is called the laser. The word itself has become so familiar that many people rarely stop to think about what makes a laser so unusual. Imagine attending a large concert. The musicians are still warming up. One violin begins playing. A trumpet follows with an entirely different melody. Someone strikes a drum. Another musician adjusts a piano. Every sound is independent. The room fills with beautiful but uncoordinated noise. An ordinary light bulb behaves in much the same way. Inside the glowing filament, countless atoms release tiny packets of light in random directions. Each wave begins at a different moment. Each has a different rhythm. Together they create the warm, comfortable glow that fills a room. Now imagine that same concert transformed. The conductor quietly raises a hand. Every musician begins at precisely the same instant. Every instrument follows the same rhythm. Every note supports the others. Instead of countless independent sounds, the audience hears one perfectly unified performance. That is much closer to the way a laser behaves. Its light waves travel together in extraordinary harmony. They share nearly the same colour. They move in the same direction. They remain synchronized over enormous distances. This remarkable order comes from one of quantum mechanics' most beautiful ideas. Under carefully controlled conditions, excited atoms can be encouraged to release light in perfect step with light that is already passing through them. Instead of producing random flashes, each atom reinforces the growing beam. One wave gently encourages the next. The result is an incredibly pure, focused stream of light. At first, even the inventors of lasers were uncertain how useful this strange new device might become. Today, it quietly touches nearly every part of modern life. Lasers carry information through the fibre optic cables that connect continents beneath the oceans. They read data stored on optical discs. They help surgeons perform delicate operations. They measure tiny distances inside advanced manufacturing systems. They scan products at supermarkets. They allow scientists to study individual atoms, and they make some of humanity's greatest astronomical discoveries possible. Among those discoveries is one of the most extraordinary achievements in modern science. For over 100 years, Einstein's theory predicted that violent events in the universe should send tiny ripples spreading through space-time itself. Imagine dropping a smooth stone into a perfectly still lake. Gentle circles spread outward across the water. Now replace the lake with the fabric of space-time. When enormous objects such as black holes collide, they disturb space-time in a similar way. The ripples travel outward across the universe at the speed of light. By the time they reach Earth, however, they have become unimaginably small. Detecting them seemed almost impossible. Scientists needed an instrument capable of measuring changes in distance far smaller than the width of an atom. The solution came from lasers. The Laser Interferometer Gravitational Wave Observatory, better known simply as LIGO, was built for this remarkable purpose. Rather than attempting to see gravitational waves directly, LIGO measures the tiny changes they produce. Its design is beautifully elegant. A single laser beam is divided into two identical beams that travel along two long tunnels arranged at right angles. Each beam reflects back and forth between exquisitely polished mirrors before returning to meet the other. If both paths remain exactly the same length, the returning light combines in a predictable pattern. But if a passing gravitational wave gently stretches one direction while compressing the other, even by an unimaginably tiny amount, the returning light changes ever so slightly. By carefully studying these changes in the interference pattern of the laser beams, scientists can detect the passing ripple itself. It is rather like watching two sets of ripples meet on a quiet pond. Even the smallest disturbance changes the beautiful pattern where the waves overlap. The laser allows those tiny differences to become visible. In 2015, after decades of engineering, patience and international collaboration, LIGO made history. For the first time, humanity directly detected gravitational waves. The signal came from two black holes that had spiraled together and emerged more than 1 billion light-years away. Their final dance released an enormous amount of energy before settling into a single larger black hole. What reached Earth was astonishingly gentle. Not a flash of light, not an explosion visible through a telescope, but a tiny vibration in space-time itself. Some scientists have described it as hearing the universe for the first time, not through sound travelling through air, because space is almost completely silent, but through the subtle rhythm of space-time itself. It has even been compared to the fading ring of a great cosmic bell, or the final note of an immense drum whose vibrations echo across the universe. None of this would have been possible without quantum mechanics. The same understanding of atoms and light that gave us lasers also opened an entirely new way of exploring the cosmos. It is a beautiful reminder that discoveries made while studying the smallest building blocks of nature often become the very tools that allow us to understand the largest structures in existence. As scientists continued exploring this remarkable partnership between quantum physics and relativity, they found themselves drawn toward an even deeper mystery. A mystery where light, gravity, and the emptiness of space itself seem to meet. It is there, near the edge of black holes, and within the quiet vacuum of the universe, that some of the greatest unanswered questions in modern physics continue to wait. There are few objects in the universe that inspire as much wonder as black holes. Even the name itself carries a quiet sense of mystery. For many years, black holes existed only as mathematical predictions. They emerged naturally from Einstein's theory of gravity, yet many scientists wondered whether such extraordinary objects could truly exist in nature. Then, during the early years of space exploration, new eyes were turned toward the universe. In 1970, NASA launched a satellite called Uhuru, whose name means freedom in Swahili. Unlike ordinary telescopes that observe visible light, Uhuru searched the sky for X-rays, an energetic form of light that often comes from some of the most extreme environments in the cosmos. Among the many mysterious sources it detected was one in the constellation Cygnus. Today we know it as Cygnus X1. At first, astronomers could not see the object directly. Instead, they watched a bright blue star quietly orbiting something invisible. The unseen companion appeared far too massive to be an ordinary star, yet it emitted no visible light of its own. As gas from the visible star spiraled inward, it became hotter and hotter, glowing brilliantly in X-rays before disappearing forever into darkness. The evidence gradually became overwhelming. Humanity had found one of its first compelling candidates for a stellar black hole. It was a remarkable moment, not because anyone had finally seen a black hole itself, but because they had learned to recognize its invisible presence by watching how it shaped everything around it. In many ways, black holes are like the wind. You cannot see the wind directly, but you can watch leaves dance across a quiet garden, or clouds drift through the sky. The movement reveals the invisible force. Black holes announce themselves in much the same way. At the centre of every black hole lies a boundary known as the event horizon. It is often described as the point of no return. Once light, matter, or anything else crosses this invisible boundary, it can no longer escape back into the universe we know. Imagine standing beside a vast waterfall. Far upstream, the river flows gently. A small boat can still turn around and safely return. But as the current becomes stronger, there comes a point beyond which no amount of rowing can overcome the rushing water. Cross that unseen line, and the journey can continue only in one direction. The event horizon is something like that invisible point. It is not a physical wall. Nothing solid marks its location. Instead, it is a boundary created by gravity itself. For many years, physicists believed this was the end of the story. Black holes swallowed everything. Nothing escaped. Nothing returned. The universe seemed wonderfully simple. Then quantum mechanics quietly complicated everything once again. To understand why, we first need to rethink another familiar idea: empty space. When most of us imagine empty space, we picture absolute nothingness, a perfectly silent void, a place where absolutely nothing exists. But quantum physics paints a gentler, far more intriguing picture. Imagine walking through a quiet forest just before dawn. Everything appears still. The air hardly moves. No leaves seem to stir. Yet beneath that peaceful appearance, countless tiny living things remain active. Insects crawl beneath fallen branches. Seeds slowly absorb moisture. Roots continue growing through the soil. Life never completely stops. The stillness is only an illusion created by the limits of our senses. According to quantum mechanics, empty space is surprisingly similar. Even what we call a vacuum is not truly empty. Instead, it is filled with restless quantum fields that never become perfectly silent. Tiny fluctuations constantly ripple through this invisible landscape. They're unimaginably brief and incredibly small, yet they remind us that nature is never completely motionless. One helpful image is to imagine the surface of the ocean on a calm day. From a distance, the sea appears perfectly smooth, but as you look more closely, tiny ripples shimmer across the water. The ocean is never entirely still. The quantum vacuum behaves in much the same spirit. It is not empty in the ordinary sense. It is alive with subtle possibilities. This extraordinary picture inspired one of the most beautiful ideas in modern physics. In the 1970s, the British physicist Stephen Hawking asked a remarkable question. What happens if quantum fluctuations occur extremely close to a black hole's event horizon? His calculation suggested something astonishing. From far away, a black hole might not be completely black after all. Instead, it could slowly release a faint glow now known as Hawking radiation. One gentle way to picture this idea is to imagine tiny bubbles briefly appearing on the surface of gently simmering water. Most bubbles form and disappear almost immediately. Nothing lasting remains. But suppose one bubble formed right beside the edge of a waterfall. Part of the bubble might be carried over the edge while the other part drifted safely away. The image is not literally what happens near a black hole, but it captures the spirit of Hawking's insight. Quantum activity occurring near the event horizon can allow energy to escape in subtle ways that classical physics never predicted. According to this picture, black holes slowly lose energy over unimaginably long periods of time. For the enormous black holes known today, this process is incredibly slow. Far longer than the current age of the universe, no known black hole is expected to disappear anytime soon. Yet the idea changed something profound. Black holes were no longer eternal prisons. They had become dynamic objects that could slowly evolve. As exciting as Hawking radiation is, it led almost immediately to another mystery. Imagine writing your life story inside a notebook. Every memory, every photograph, every letter. Now imagine placing that notebook into a fire. When the flames finally die away, where has the information gone? In everyday physics, the information is not truly destroyed. It becomes extraordinarily scrambled within smoke, ash, heat, and the surrounding air. In principle, the information still exists, even if recovering it would be practically impossible. Quantum mechanics strongly suggest that information should never simply vanish from the universe. But if a black hole eventually evaporates through Hawking radiation, what happens to everything that once fell inside? Does the information somehow escape? Does it remain hidden forever? Or does our understanding of quantum mechanics need to change? This puzzle is known as the black hole information paradox. Despite decades of research, physicists still debate its solution. Some ideas suggest that information may be subtly encoded within the escaping radiation. Others propose that it may be preserved in ways we do not yet fully understand. Still others point toward entirely new descriptions of space and gravity that have yet to be completed. What makes this mystery so fascinating is that it sits at the meeting point of humanity's two greatest theories. Einstein's theory of relativity describes gravity with extraordinary success. Quantum mechanics describes atoms and particles with equal brilliance. Separately, each theory has transformed our understanding of nature. Together, near black holes and the beginning of the universe, they begin to disagree. It is as though two beautifully detailed maps describe neighbouring countries perfectly, yet refuse to align where the borders meet. Somewhere beyond that border, a deeper map almost certainly exists. Physicists often call this hoped-for understanding a theory of quantum gravity. No one yet knows exactly what form it will take. Perhaps future generations will discover it. Perhaps the clues are already quietly hidden within observations we have not yet fully understood. Until then, black holes remain more than extraordinary objects scattered across distant galaxies. They have become natural laboratories where the deepest questions in science quietly gather. They remind us that every great discovery opens the door to even greater mysteries. And despite all these unanswered questions, humanity has already learned enough from quantum mechanics to begin building entirely new kinds of machines that no longer simply obey the quantum world, but deliberately harness its strange behaviour to solve problems that once seemed impossible. For much of the 20th century, quantum mechanics was something scientists used to explain nature. It helped us understand why atoms remained stable, why chemical reactions occurred, why lasers produced such remarkable light, and why atomic clocks measured time with astonishing precision. Quantum mechanics was a language for describing the universe. Gradually, however, something remarkable happened. Scientists began asking a different question. Instead of simply observing quantum behaviour, could they learn to guide it? Could they persuade nature's smallest building blocks to work together in carefully controlled ways? That question quietly marked the beginning of what many researchers now call the second quantum revolution. The first revolution taught humanity how the quantum world behaves. The second is teaching humanity how to work alongside it. To appreciate why this matters, it helps to think about the computers surrounding us today. Whether you're holding a smartphone, using a laptop, or operating a powerful supercomputer, every one of these machines speaks the same basic language. It is a language built from tiny electrical switches. Each switch can be in one of two conditions. You can imagine them simply as yes or no, on or off, like a light switch resting against a wall. These tiny switches are called bits. Every photograph, every email, every song, every movie, every map, everything stored inside today's computers is ultimately built from unimaginably large collections of these simple choices. 1 or 0, yes or no. It is an extraordinarily successful system. Modern civilization would scarcely function without it. Yet nature, as quantum mechanics revealed, is capable of something richer. Imagine walking into a vast library. A classical computer is rather like a careful librarian who examines one shelf after another, following an organised path until the correct book is found. The librarian is wonderfully efficient, but there is still only one search taking place at a time. Now imagine something different. Instead of opening only one path through the library, imagine exploring a landscape of possibilities before gradually narrowing toward the best answer. The comparison is not perfect, but it hints at the remarkable flexibility that quantum mechanics offers. The basic unit of a quantum computer is called a qubit. Like the word bit, the name may sound technical, but the central idea is surprisingly gentle. An ordinary bit must always settle into one definite condition. A qubit, however, can make use of quantum superposition. Rather than being limited to only one simple state before a calculation unfolds, it can exist in a carefully controlled combination of possibilities. Earlier, we compared superposition to a melody waiting to be played. That image is helpful here as well. Imagine an orchestra preparing for a performance. Before the conductor raises a hand, countless musical possibilities still exist. The score has not yet unfolded into one particular performance. Similarly, a qubit allows a quantum computer to explore possibilities in ways that classical bits cannot. This does not mean that a quantum computer magically tries every answer simultaneously. That is one of the most common misunderstandings. Instead, carefully designed quantum algorithms guide the probabilities so that useful answers become increasingly likely, while less useful possibilities gradually fade away. The process is subtle, elegant, and remarkably different from ordinary computation. Another uniquely quantum resource also becomes important: entanglement. As you learned earlier, entangled particles behave not simply as isolated objects, but as parts of one larger quantum system. Inside a quantum computer, carefully created entanglement allows groups of qubits to work together in ways that have no true classical equivalent. It is rather like listening to an orchestra once again. A single violin can perform a beautiful melody, but when dozens of musicians perform together in perfect harmony, entirely new musical textures become possible. The power comes not only from the individual instruments, but from their relationships. Quantum computation follows a similar philosophy. The relationships between qubits become just as important as the qubits themselves. Of course, turning these beautiful ideas into real machines has proven extraordinarily difficult. Quantum states are delicate. Even tiny disturbances from the surrounding environment can disrupt them. A slight vibration, a wandering magnetic field, a little too much heat. Almost anything can disturb the fragile quantum behavior that researchers work so carefully to preserve. Imagine trying to balance a single snowflake on the tip of your finger during a warm summer afternoon. The snowflake is real. It can exist, but maintaining it requires exceptional care. Quantum information is similarly fragile. For this reason, many quantum computers operate at temperatures unimaginably colder than the coldest winter ever experienced on Earth. Special refrigeration systems cool the quantum chips until almost all thermal motion becomes quiet. The goal is not to freeze the computation itself. It is to create an environment calm enough for delicate quantum states to survive long enough to perform useful work. Even under these carefully controlled conditions, errors remain one of the greatest challenges. Researchers devote enormous effort to quantum error correction. The name sounds intimidating, but the idea is familiar. Imagine copying an old handwritten manuscript. Occasionally tiny mistakes appear. A letter is skipped. A word is repeated. If several careful copies exist, those errors become much easier to identify and correct. Quantum error correction follows a similar spirit, although it must do so while respecting the unique rules of quantum mechanics. It is one of the great engineering achievements still unfolding today. Because these machines remain so challenging to build, people sometimes imagine that quantum computers will soon replace every laptop and smartphone. In reality, that is almost certainly not their future. A quantum computer is not simply a faster version of the computer sitting on your desk. It is a different kind of tool. Much as a telescope does not replace a microscope, quantum computers will not replace classical computers. Each excels at different tasks. Many everyday activities, writing documents, browsing the internet, watching videos, or playing games, are already handled beautifully by classical machines. Quantum computers are expected to shine in very different areas. They may help scientists simulate molecules that are too complex for ordinary computers to model accurately. That could accelerate the discovery of new medicines. They may help researchers design advanced materials with remarkable properties. They may improve optimization problems involving enormous numbers of possibilities, from transportation networks to energy systems. They may deepen our understanding of chemistry, superconductors, and even the quantum behavior of nature itself. Perhaps one of their greatest strengths will be working alongside classical computers rather than replacing them. The future may belong to teams of machines, classical computers managing familiar everyday tasks, artificial intelligence recognizing patterns and assisting human creativity, quantum processors tackling highly specialized problems that benefit from uniquely quantum behavior. Each contributes its own strengths, much like different musicians performing together within the same orchestra. We are still in the early years of this technological journey. Today's quantum computers remain experimental. They are improving steadily, but many scientific and engineering challenges still lie ahead. History, however, offers a gentle reminder. The first electronic computers filled entire rooms. They performed calculations far more slowly than even an inexpensive smartphone does today. Few people could have imagined how dramatically those machines would transform civilization. Perhaps quantum technology is now standing at a similar beginning. The greatest discoveries may still lie quietly beyond the horizon, and if history has taught us anything, it is that today's mysterious laboratory experiments often become tomorrow's ordinary tools, quietly woven into everyday life in ways no one could have fully imagined. As remarkable as these machines may become, they're only one part of a much larger story. A story that ultimately asks not only what quantum mechanics can build, but how it may continue to reshape humanity's understanding of reality itself for generations yet to come. As every great scientific journey unfolds, there comes a moment when the questions become even more fascinating than the answers. Quantum mechanics has already transformed the modern world in ways that would have seemed almost impossible just a century ago. It explains why atoms remain stable. It allows lasers to illuminate the hidden corners of the universe. It keeps atomic clocks measuring time with astonishing precision. It helps your phone quietly determine its location. It has revealed gravitational waves and opened entirely new windows into the cosmos. Yet many scientists believe we're still standing near the beginning of the quantum age rather than its destination. The next chapters of this story may unfold not only inside laboratories, but quietly throughout everyday life. One promising direction is something known as quantum sensing. Every measurement we make is limited by the sensitivity of our instruments. The more precisely we can measure nature, the more clearly we can understand it. Quantum mechanics offers remarkable new ways of building sensors that respond to incredibly tiny changes in the world around them. Imagine walking through a dark forest at night. To your eyes, everything appears still. Then the moon emerges from behind the clouds. Suddenly, faint paths, distant trees, and gentle movements become visible. Nothing in the forest has changed, only your ability to see it has improved. Quantum sensors promise something similar. They do not create new features of reality. They simply allow us to notice details that were always present but previously hidden from view. Scientists hope these instruments will measure tiny variations in Earth's gravitational field with extraordinary precision. Such measurements could improve our understanding of underground water supplies, volcanic activity, and even subtle movements beneath Earth's surface. In medicine, quantum technologies may one day detect biological signals that are currently too faint to observe, allowing doctors to recognize disease much earlier than ever before. Navigation may also evolve in remarkable ways. Today, much of the world depends on satellite navigation systems. These systems are extraordinarily reliable, yet they depend upon signals traveling across space. Future quantum navigation devices may allow ships, aircraft, and even spacecraft to determine their positions with far less reliance on external signals. Instead, they could make use of exquisitely sensitive quantum measurements, performed entirely within the vehicle itself. Such systems are still being developed, but they illustrate a broader pattern that has appeared throughout this documentary. Again and again, ideas that once seemed purely theoretical have quietly become practical tools. The same may prove true for communication. Earlier, we explored the idea of a quantum internet built upon entanglement rather than classical information alone. Although this technology remains in its early stages, researchers have already demonstrated important milestones. Entangled particles have been shared across cities, across mountains, even between orbiting satellites and ground stations. Each experiment brings us one small step closer to networks capable of distributing quantum information over ever greater distances. If such networks eventually become widespread, they may enable forms of communication and collaboration that are difficult to imagine today. Yet perhaps the greatest impact of quantum technology will not come from any single invention. It may come from the way different technologies begin working together. History offers many examples. Electricity alone transformed civilization. Computers transformed civilization. The internet transformed civilization, but their greatest influence emerged when they combined. The same may happen again. Classical computers may continue performing billions of familiar tasks every second. Artificial intelligence may help recognize patterns hidden within enormous collections of information. Quantum processors may solve specialized problems involving chemistry, materials, optimization, and simulation. Instead of competing, these technologies may quietly complement one another, each contributing strengths that the others do not possess. And still, even after all these achievements, the deepest scientific questions remain beautifully open. Why does the wave function appear to collapse during measurement? Or does it collapse at all? What is the most accurate interpretation of quantum mechanics? Does nature continuously branch into many possible histories? Are there hidden structures we have not yet discovered? Or are probabilities truly woven into reality itself? No experiment has yet provided a final answer. Then there is perhaps the greatest challenge of all. How can quantum mechanics and gravity finally be united into one consistent description of nature? As we explored near black holes, Einstein's description of gravity and quantum mechanics each work astonishingly well within their own domains. Yet, where gravity becomes extraordinarily strong and distances become unimaginably small, the two theories no longer fit together perfectly. Some researchers explore string theory. Others investigate loop quantum gravity. Still others pursue entirely different ideas. Each approach attempts to reveal a deeper level of reality, one from which both gravity and quantum mechanics naturally emerge. No one yet knows which path, if any, will ultimately succeed. That uncertainty is not a weakness. It is one of science's greatest strengths. Science is not a collection of permanent answers. It is a continuing conversation between human curiosity and the universe itself. Every discovery invites another question. Every solution reveals another mystery waiting quietly beyond it. Perhaps that is why quantum mechanics continues to captivate scientists after more than a century. It refuses to become ordinary. Even after countless successful experiments, it still challenges our intuition in ways that few other scientific theories ever have. And yet, history suggests something fascinating. Ideas that once seemed completely impossible often become wonderfully familiar. There was a time when electricity seemed mysterious, a time when flying across oceans appeared unimaginable, a time when carrying a library, a camera, a map, and a telephone inside a single pocket-sized device belonged only to dreams. Today, they are simply parts of everyday life. Perhaps future generations will feel the same about quantum mechanics. Children may grow up surrounded by quantum technologies without giving them much thought. Secure quantum communication may seem as ordinary as wireless internet does today. Quantum sensors may quietly improve medicine and environmental science. Quantum computers may become trusted partners for solving specialized scientific challenges. and words like superposition and entanglement may one day sound no more mysterious than electricity or magnetism. As our journey gently comes to rest, it is worth returning to where we began. A quiet room, a soft light, a clock patiently marking the passing moments. Perhaps your phone rests nearby, silently connected to satellites guided by atomic clocks born from quantum physics. Perhaps a beam of laser light is carrying information beneath an ocean somewhere, linking distant continents together. Perhaps far beyond the night sky, two black holes are slowly circling one another, sending delicate ripples through space-time that will continue travelling across the universe long after we're gone. All of these seemingly unrelated stories are connected. They remind us that the smallest discoveries can reshape the largest ideas, that by studying the tiniest building blocks of nature, humanity has uncovered a universe more subtle, more beautiful, and more deeply interconnected than anyone once imagined. And perhaps that is the most comforting thought to carry with you into the quiet hours of the night. The universe has not become less understandable because of quantum mechanics. It has become richer. Every answer has revealed another layer of wonder. Every mystery has invited another gentle question. As you begin to relax, perhaps even drifting towards sleep, you can leave those questions exactly where they belong, in the quiet company of the stars still waiting patiently for curious minds to return. Until then, may your thoughts become as calm as a still lake beneath the night sky, and may the quiet rhythm of the universe accompany you into a peaceful rest. Good night.